Hi students, welcome to Inside Physics. Today we will discuss some problems on current electricity which are very important for JEE Mains and advanced and other competitive engineering entrance examinations. So here we'll see first problem. For a wire R by L is equal to 1 by 2 and the length of the wire L is equal to 5 centimeters. If potential difference of 2 volts is applied across it, then current through the wire will be. Here there is a wire of length 5 centimeters. So 5 centimeters is the length of a wire, assume as AB. So it is in centimeters, so we need to convert it into meters. So length is equal to 5 centimeters, that is equal to 5 into 10 to the power of minus 2 meters. Here R by L, where R is resistance of the wire. For any conductor there will be a resistance which is mentioned in ohms. So R by L is equal to 1 by 2 is already given. Relation between length of the wire and resistance. So R is equal to L by 2. What is L? 5 into 10 to the power of minus 2 meters by 2. So 2.5 into 10 to the power of minus 2 ohms. This is the resistance of the wire where L is 5 centimeters, which is length of the wire. Now what is asked in this? Then the current through wire will be. We know that according to Ohm's law, there is a conductor and it has a current flow, means there must be a potential difference across it. What is the potential difference across the conductor? 2 volts. So according to Ohm's law, we know that V is equal to IR. That implies I is equal to V by R. So V already given as 2 volts, 2 by resistance calculated 2.5 into 10 to the power of minus 2. So this will be in amperes. So if 10 power minus 2 will be moving up, means 100 by 2.5. That means 2.5 into 40 times. So 2 into 40 is equal to 80 amperes. This is the current flowing through the conductor AB, which is of length 5 centimeters, when a potential difference of 2 volts is applied across the conductor. Okay, then we will see the next problem. So here we will see the second problem. A wire of resistance 8 ohms is stretched to twice its original length, then the resistance of stretched wire would be. Suppose if you consider a wire AB of length L, say this is having a resistance of 8 ohms. So we know that resistance of a conductor or wire is equivalent to rho L by A, where rho is resistivity of the wire, L length of the wire, A area of cross section. Here what is given? The wire is stretched to double its original length. That means if you consider the resistance after stretching the wire, do you think that it is increasing or decreasing? The resistance of the wire, you mention in the comments before getting the answer, that if you stretch the wire, it becomes thinner and thinner, resistance will increase or decrease. We will calculate here and we will know how it will be. If R dash is the resistance after stretching, the length has become 2L, and in order to maintain the volume of the wire always constant, the area of cross section will become half. Okay, now we see that here the 2 will go up and it will become rho L by A, that is equal to 4 into R, where R is already given as 8 ohms. So what it has become, 4 into 8, 32 ohms. So to maintain the volume constant, the area of cross section will become half of the original cross section. So by these two changes, the resistance has increased 4 times. So that logically we can say from this, the wire will become thinner, resistance will increase. So next we will see the third problem. Now we will see the third problem. A potential difference of 100 volts is applied to the ends of a copper wire of length 1 meter. What is the average drift velocity of electrons? We know that whenever there is a flow of electrons in a conductor, by applying potential difference across its ends, the electrons are accelerated because of the potential difference, and the electrons will collide with the atoms or ions or molecules in the material. So the drift velocity is, the meaning is they are drifting towards the positive end of the electric field because they are negatively charged. So the drift is because of the potential difference. So how to calculate the average drift velocity? As per the formula we know, average drift velocity is equal to NCUEA. We will see the terms what it is. Current flowing through the conductor, number of free electrons of copper per unit volume into charge of electron into area of cross section of the copper wire. So this gives us the drift velocity. So here 100 volts is applied and the length of the conductor is 1 meter. So we know that the electric field, whenever there is a potential difference, there is an electric field developed across the conductor, and that electric field, as per the relation with potential difference, we know that V by R. R is the distance between the two ends of the conductor, here that is 1 meter. So V by 1, that is equal to 100 by 1 volts meter, that is equal to E is equal to 100 volts per meter. Okay, so here we know that current density J is given by sigma E, where sigma is given here. Take sigma as this value and number of free electrons of copper per unit volume is this. So sigma is conductivity. So whenever there is a resistivity for a wire, the reciprocal of resistivity is called conductivity. Conductivity multiplied by electric field gives current density, which is nothing but current flow per unit area of cross section. So here I by A can be taken as sigma E. I by A can be taken as sigma E. Sigma E by number of copper free electrons into charge of electron. Now if you substitute these values, take sigma, the conductivity of copper wire, as 5.81 in 10 to the power of 7 into electric field is 100 volts per meter, and the number of free electrons is already given in the data, 8.5 into 10 to the power of 28, and into charge of electrons we already know, into 10 to the power of minus 19 coulombs. So finally the value, if you calculate by mathematical formula, you can get the value as 0.43 meters per second. 0.43 meters per second. This is the drift velocity of electrons in a copper wire whenever there is a potential difference of 100 volts and the wire length is 1 meters. Okay, then we'll move to the next problem. Fourth problem. A current of 2 milliamperes was passed through an unknown resistor which dissipated a power of 4.4 watts. Then, what is the dissipated power when an ideal power supply of 11 volts is connected across it? So, here there is a case where an unknown resistor is having 2 milliamperes of current passes through it. So we know whenever there is a conductor there must be a resistance, so that resistance will cause the wastage of power dissipated. That means the 4.4 watts is wasted while the 2 milliamperes current is flowing through an unknown resistor. Then the question is, what is the dissipated power when 11 volts is connected across that resistor? So we know that power is equal to I square R. This power dissipated is equivalent to heat produced according to Joule's heating effect, and it is also multiplied with time when the time is also time of flow of current is also considered. Here what is the current? I is equal to 2 milliamperes. So we need to convert this as amperes. So 10 to the power of minus 3 amperes is the current. So resistance is unknown. We don't know R. So power dissipated is equal to 4.4 watts. So we have the data, current and power. We can calculate the resistance of the unknown resistor. Now here R is equal to P by I square, that means 4.4 by I 2 into 10 to the power of minus 3 whole square, that means 4.4 into 4 into 10 to the power of minus 6. This is the resistance. So we will keep this as it is. And next, what is asked? Power supply of 11 volts is connected across it, and then what is the power dissipated? We again have another formula for power. If you put I is equal to V by R, this power is again can be written as V square by R. Here we know that V is equal to IR as per Ohm's law. I is equal to V by R. If you put V by R in place of I, power can be written as V square by R. Then what is the potential difference applied across the resistor? 11 volts. So 11 square, that means 11 into 11 by resistance is nothing but 4.4 by 4 into 10 to the power of minus 6. So this must be calculated as 11 into 11 by 4.4 into 4 to 10 to the power of 6, 10 to the power of minus 6. Okay. So this numerator has gone to this denominator has gone to the numerator, and we can write that value. So if you calculate the value as resistance, and what is the final value for it? We will get the final value as 11 into 10 to the power of minus 5 watts. Power is equal to 11 into 10 to the power of minus 5 watts. So this 4.4 into 10 to the power of minus 6. So this 11 can be taken into consideration. So this is the power dissipated when 11 volts is connected across the resistor of resistance this much. Ohms is the resistance. See the fifth problem in this session. A uniform metallic wire has a resistance of 18 ohms and is bent into an equilateral triangle. then the resistance between any two vertices of a triangle is, any two vertices of the triangle is. So here a wire, metallic wire, we don't know the length of the wire, but the total resistance of the wire is given as 18 ohms, and it is bent into an equilateral triangle. Okay, so then the resistance between any two vertices, now this wire is converted into a triangle shape which is equilateral. So if you consider an equilateral triangle and name it as A, B, C or the vertices, so the resistance offered by total wire is 18 ohms. So each side of the triangle, say some part of this wire will be 6 ohms, and this is also considered to be a 6 ohm resistor side, and this is also considered to be a 6 ohms. The total considered as 18 ohms, and total length of the wire is having a 18 ohm resistance. Now the question is, what is the resistance between any two vertices? We take it as AB or BC or AC. So if you consider the resistance between the two vertices, say BC, what can we do with this diagram to measure the equivalent resistance? Okay, so we consider this, to consider these two as two resistors, and see, to have a better idea, we will take this as E and point E and F. Okay, so what is the equivalent resistance? If you observe, these two sides are in series, right? This resistor is in series. So what is the formula to calculate the equivalent resistance when the resistors are connected in series? That is 6 plus 6. That means R1 plus R2. If you consider as R1 R2 as two resistors, the equivalent resistance is sum of the two resistors. So this is 12 ohms. Okay, R equivalent for these two sides is 12 ohms. So this diagram can be converted to an equivalent resistance of 12 ohms, and it is connected to another resistance of 6 ohms. This 6 plus 6 12, this is converted to single resistor, and this is a 6 ohm resistor here, and these are the points A, E and F again. So this diagram is converted into this equivalent circuit where these two resistors are in series, so the resistors are added. If you observe this circuit, these two are in parallel. So R equivalent for parallelly connected resistors is nothing but, we can write it as equivalent resistance as 1 by R equivalent is equal to 1 by R1 plus 1 by R2. Here what is R1? You consider R1 as 12 and R2 as 6. Here 1 by 12 plus 1 by 6. So here it is equivalent in series, this is equivalent resistance in parallel. So 12 into 6, you take LCM, this is nothing but 6, and this is considered as 12. Okay, so when you calculate the final value, what you will get? So 12, 18 by this 1 by R equivalent. Okay, so this is 1 by R equivalent, Then what is this? If you calculate this one, what you will get? That implies R equivalent is equal to 12 into 6 by 18. 12 into 6 by 18. So if you calculate that one, the value will be 4 ohms. This is 4 ohms. Okay. Now this is the way to calculate the equivalent resistance when these kind of resistors are connected whether in series or parallel, or by the diagram we can simplify the diagram resistors and we can calculate whether they are in series and parallel by logic. Okay, so we'll move to the next problem in the next video.